Hey there. So another day, another round. We've got Codeforces Round 725, and I'm going to leave the problems on a separate screen just to be quicker. Bring them back afterward. And you can find the link in the description. Okay. Oh, I see. It's actually a little tricky. Okay, so otherwise it's just the got G. Okay. Okay. So right. Yeah. Oh, no, that's not what we want. No, this is still, okay, that makes sense. A, B, take C and replace A with A C. Just wait. Oh, exactly. Exactly K turns. That is kind of weird. So yes. So basically, we need to find, well, the shortest number is generally, oh, it could be 1, it could be 0, 1, or 2. Right, we just need to like count the prime factors. Take the GCD. Need to at least do that. And then we just need, we just need like, we just need these factors too. To the 4th times, I guess we can, we do this is fine. Okay, so then Oh, this is weird. That is a special case. Oh, if k is equal to this minus 1, then we have a problem? No. No, it's fine. Haha, last assignment. Okay, so you can go exponential here. So, is E the hardest problem? Or changed it. So it's just the number of nines. Plus 1. Alright, I'll do F. Are they all test case problems? Yeah, they are. Because our development base tells me how many. Yeah, I think that's right. Cool. Going to G. I think E is the hardest problem. Here, red candies and B. Blue candies are. Oh, I get it. Okay, so it's X and Y, and then these B, but those can be swapped around. And it's like, oh, okay, so. And that's J plus K. Okay, so obviously. X plus Y. Yeah, I see. So we have 6 and 10. 1, 3. We can do 3, which is 3 and 1. Third. Do times 2, and then you end up with 4. guess, okay. The x divided by is that it? This one. Right. Yeah, you should actually. Oh, you. Yeah, if A equals B, then we don't really have much of a decision. We're just going to do this. So this is not what we want. So I think what we're going to do is we're just going to I guess we're going to try this as close as possible. The way we're going to do that is oh, is it a ternary search problem? Do you just search out J? Min of that. Alright, we just have problem E left. So, this string is going to be very long. I think it's just this. The last thing you do, how many ha-has you create? Well, it's just going this thing plus this. now you just want to know, like, oh, I think I get every string is the first three, last three, and the number of ha-has in a row. First three, last three, number of ha-has in a row. See, the first is gonna be. then post the line. I'll help us all. First. Trim and then returns. Alright, about to submit. I actually got 32 instead of 31, but it doesn't matter. Put me at 91. Let's see. Let me try the ternary search sheet. Alright, we got it, and that puts us first. Let me see, so XRB, go the other way. See, okay, I guess we'll just do that. Oh, that's funny. So that's actually wrong. Why is that wrong? Oh, maybe we should solve it for the loading point. Right, that makes sense. That's wrong actually. Does this help? I see. So, okay. Right, because you can have equal things for a while, and then it gets better, and then it gets equal again, and you don't know which way to go. Oh, yeah, well, anyway. Fine. Well, this person was quite fast on finishing. But it didn't make sense to do E until the end. Yeah. Let me see. Is there anything I want to change or check? Yeah, well, this was kind of dumb. I could have just done that. Oh, I guess I could even do that one. We'll get it wrong if we don't. Yeah, okay. E T. Oh, right. How long does T take? Ninth. So. How does runtime work? If B is less than oh. Okay, I'm just gonna back to this over now. And wait, what happened? Oh. Takes 0.1 seconds, which I guess is alright. That is awfully. Oh, you can solve this in cube instead because you just need this sum. And then you use. I think you use Miller-Raven. It's so advanced. Yeah, and then if you just did you factoring, that would be too slow. I don't know what they're trying to do here. It's kind of weird. Okay, so there's about an hour left of the contest, and yeah, what I'll do is I'll go over each of the problems, explain my approach, and just go over my thought process for each of them. So let's start with problem A. In problem A, basically there's this whole story, but what you really have going on is you have an integer n that's between 2 and 100, and you have this array which is a permutation of 1 through n, and you need to destroy both the 1 and the n, and in particular the only thing you can do is either pick the leftmost stone and destroy it, or pick the rightmost stone and destroy it. And you want to know the fewest number of moves you can take to accomplish your goal. So for this kind of array, because 1 and n are right here on the left side, you would just do the leftmost stone twice, and the answer would be 2. So in general, for this type of situation, you're going to have, something like this. Maybe this is your array, and then maybe 1 is here, and then n is here, right? So basically you have 3 different options. The first option is you can just go from the left and destroy all of these like that. The second option is you can go from the right and destroy all of these like that. And then there's actually a third option where you destroy from the left to get to here, and you destroy from the right to get to here. And we're just taking the min of those 3 options, and that's basically what our code is doing. So the code just goes through the array, finds the 1, finds the n. It actually doesn't matter which is which, so I just make sure their positions are in order. And then you can either go all the way to the big from the left, you can go all the way to the small from the right, or you can do this one, which does the left side and right side. And yeah, so that's how we do this problem. So let's talk about problem B. So problem B, basically we're given a bunch of amounts of candies that we need to, that each friend starts with. And we need to pick a set of friends and kind of redistribute their candies among the friends. And you want to end up with all friends having the same amount of candy. And we want to, if we can do that, if we can't do that, we print -1. But if we can do that, we want to know the minimum number of friends we can pick to redistribute their candies and get this all equal situation. So for example, if the candies amounts are 4, 5, 2, 5, we just pick the 2 5s, take 1 from each, give them to the 2, and then you get 4, 4, 4, 4. And you've only picked 2 friends, so that is the minimum. So this problem, pretty simple, just a couple observations. So first of all, if the sum of the number of candies is not divisible by n, then it's not possible, because we know that sum divided by n is the amount that everyone has to end up with. And so yeah, obviously that has to be an integer. So that's the first thing we would check. If sum is not a multiple of n, then the answer is -1. Otherwise, it is always possible. And in fact, all we have to do is, for example, in this case, let's look at the average. The average is 4. Well, clearly for everything bigger than 4, for these 5s, we need to pick them, right? Because we need to reduce their count. But it turns out picking everything strictly bigger than the average is exactly what we want to do. It's also the minimum. And that basically gives us our answer. So we find the average, and we just count the number of values in A that are above that average. And those are the people who we will kind of take from and redistribute. Yeah, so pretty simple, just 2 main observations. First, the divisible by n, and then the greater than average. All right, so problem C. Okay, problem C, you've got an array A of n integers. You want the number of pairs ij, where I is less than j, and the sum of ai plus aj is greater than or equal to L, and it's less than or equal to R. So it's between L and R. And n is pretty large. It's up to 2 times 10 to the 5th. So we can't do any, double nested ij loop for an n² solution. That's too slow. So for this type of problem, the first observation you can make is, hey, let's just solve the problem for R. So if we just solve, if we ignore this part, if we only solve this part, how many ij pairs are less than or equal to R, then we can solve the problem because we just, let's say we have a function to count for just R. Then we would take the function, call, count for R, and then what we would do is we would subtract out count for L minus 1. Because we want the things that are less than or equal to R, but we want to subtract out the things that are less than or equal to L minus 1. So that's nice because it helps us kind of cut the problem in half. So now we're just getting the number of pairs ij, where ai plus aj is less than or equal to R. The other thing here is, even though it specifies I less than j, because this ai plus aj is symmetric, we can just reorder the array however we want, and the pairs will still be the same. So we can just sort the array. And so now we have a sorted array, and now we're just trying to figure out how many pairs ij satisfy ai plus aj is less than or equal to R. And this turns out to be a pretty standard two-pointer sweep problem. So again, do all that, sort. Yeah, and then the main idea here is I start I at 0 and I start j at n minus 1. And basically, as I increases, j will have to decrease. So if ai plus aj, while ai plus aj is too big, I'll move j down. And then basically, j for this particular I can be anything between I plus 1 and the actual variable j. So that gives us j minus I choices. And because of how this nested loop works, this amortizes to O of n, because this j minus minus can only happen at most n times in the entire loop. And so yeah, then we just do the thing we mentioned, we count for R and we subtract the count for L minus 1. All right, so that is problem C. And here, problem D. So this one was a little bit tricky. You've got two integers a and b, and in one turn you can do either of these two operations. Take an integer c greater than 1, and a should be divisible by c, and then just divide a by c, or do the same thing with b. And the goal is to make a and b equal using exactly k terms. So it has to be exactly k terms. That's a key thing here, and that makes it a bit tricky. You're given up to 10 to the 4th test cases with a, b, and k. A, b, and k are between 1 and 10 to the 9th, and you want to determine whether it's possible to make them equal using exactly k terms. So they give an example with 36 and 48. First you can divide 48 by 6, then you can divide 36 by 2, and then you get these numbers. Then you divide 18 by 9, you get 2 and 8. Then divide 8 by 4, and you get 2 and 2. So first of all, what I thought about was, what is the minimum number of operations to make them equal? And well, that's not too hard to do if you think about the prime factorization. So basically any sort of factor that's in A that's not in B has to be removed, and any factor that's in B that's not in A also has to be removed. So kind of the optimal number to get to is their GCD. And so that's kind of the first thing that I did here. So first take the GCD, and then the minimum number of operations we need is, we need one operation if A is greater than G to get down to G. We need another one if B is greater than G to get down to G, right? So for example, if, let's say the GCD is 5, and then A is 10, B is 15. Well, we need one op to get A from 10 to 5. We need another op to get B from 15 to 5. So that's 2 ops. So 10 and 15 is 2 ops. But if we had 10 and 5, it's just 1 op, because we just need to get 10 down to 5. We don't need to change B at all. And so that's what this is doing here. This gives us the minimum number of operations, and if k is less than that minimum, then we cannot make a and b equal. So that's one key observation. Otherwise, the only tricky case is if a equals b and k equals 1. It's not possible because they're already equal, but we have to do an operation that makes them not equal. So yeah, that's kind of a tricky thing there. Just make sure to catch that. It's actually in the samples, which is nice. This last sample right here. Yeah, and then otherwise, really the main problem we have actually with doing it in exactly k turns because as long as we have enough terms, k is at least the minimum, then we can generally do it, except for the fact that every time we do an operation, we're reducing a and b significantly. So in particular, the largest number of operations we can do is basically to divide a and b by a single prime each time. So again, if we have the 10 and 15, the most operations we can do is 4, because this is 2 times 5 and this is 3 times 5. So, we can divide a by 2, then divide b by 3, then divide a by 5, then divide b by 5, and then that's it. We're down to 1, 1, and we can't do anything else. So that's 4 operations. So if k is more than that number of operations, then we cannot do it. But it turns out if k is at most, like in this case, if k is at most 4, and we already checked k is at least 2. If k is at most 4, then we can do it. And the reason is, basically we can think about having these operations, right? A divided equals 2, b divided equals 3, a divided equals 5, b divided equals 5. And so this is 4 operations, right? So we can definitely do it with 4 operations. But if we want fewer than 4 operations, let's say we want, 3 operations, we can just take any 2 of these for the same variable, for example, these 2, and we can just squeeze them into 1. So b divided equals 15, right? And if we want 2 operations, we can also do that here. And so, yeah, we can get any number between this minimum and the sum of the number of primes. So all we have to do really here now is calculate the sum of the exponents on the prime factorizations. And yeah, I have some pre-written code to do that. I do a sieve, basically do a sieve up to square root of 10 to the 9th, and then I just check all the primes between 2 and that square root and try to divide through them, and that will give me the prime factorization. And I just add all of the exponents, and that tells me the number of primes. So for example, if you have 7 squared times 11, that's 3 primes because you have 7, 7, 11. Yeah, so that's the key to this problem. The runtime, it's a little bit scary, but it ends up being fine. My solution was about 592 milliseconds. So it seems like you definitely did need to do this, this kind of sieve and pulling out all of these primes in advance. I think based on these numbers, I don't think you have enough time to just loop from 1 to square root of a and square root of b. I think that is too slow, because my solution is already over, it's already close to 30% of this time limit. So you don't have a ton of leeway there. In particular, my solution is a log factor faster than just looping up to the square root. The reason is that the density of primes is 1 over log. So that helps make it faster. And that makes it kind of a tricky div3 problem. That's not a super duper easy thing to do. And funny thing is, it actually turns out you can do this problem in cube root runtime. The reason is you don't actually need to find the exact factorization. You just need to know the form of the factorization. So if you check all of the numbers up to the cube root of 1e9, so if you check all the numbers up to 1000 and try to divide that out, and you're still left with some amount, then what you can do is it's either, because you've gone up to 1000, it's either p times q or it's the prime itself p. And then you can run Miller-Rabin to determine whether it's prime or not, and that gives you the basically the form of the prime factorization. It's kind of a tricky thing. It's definitely too advanced for div3 to implement Miller-Rabin. Kind of ridiculous actually, but that would be something that makes this much faster. Now I'm wondering if I have, if there's something that I missed here where there's actually a much faster solution. It does look like there are people with significantly faster solutions here. I wonder what, I actually wonder what they did. I guess I can't see for now, but maybe we'll find out later. Definitely the cube root solution will be quite fast, but I don't really think anyone should have done that because it takes a lot more effort. Maybe if you have Miller-Rabin pre-coded, it's not too bad. But anyway, let's keep moving. So, okay, so E is actually the hardest problem in this problem set. So I'm going to go out of order a bit. I'm going to talk about F and G, and then I'm going to talk about E. In fact, F actually has more solves than D. So that kind of confirms what I was thinking about D being actually pretty hard, especially in a diff 3. Okay, so problem F, you've got two integers L and R, and L is less than R, and we're going to add 1 to L until we get to R. So we're going to add 1, exactly R minus L times. For each time, we look at the number of digits that are changed. So for example, for 909, when we add 1, we get to 910, and these two digits are changed. When we add 1 to 9, the result is 10, and again, 2 digits are changed. So we do count this new 1 because there was kind of an implicit 0 before. And then if we have 489999, then the result is 490,000, and these are 5 digits changed. And it's always, it's always gonna be a suffix of the results. And yeah, we just want to know, given L and R, what is the total number of changed digits? So the thing is, L and R go up to 10 to the 9th, so we cannot simulate this process and just count it. And there's actually 10 to the 4th test cases, so it's definitely too slow. But we can apply the same thinking that we did before, where, problem C, where we had L and R and we're counting things. Here we can just apply it because we can write a function, let's say f of R equals the number of digit changes between 0 and R. So we're starting from 0 and we're going up to R. What is the number of digit changes? Well then, again, the answer to the problem that we actually want is just going to be this. So now we can separate L and R, which is nice. We can just compute this separately. So how do we compute the number of digit changes from 0 to R? So we're starting from 0 and we're incrementing until we get to R, and we want to count the number of digit changes. Well, if we're thinking about this form, basically what we know is that, okay, which are the numbers where 5 digits are changed? Well, it's the numbers that have 4 9s at the end, or after you add 1, it has 4 zeros at the end. Okay, so now if we think about, how many of those are there, that's a lot easier to think about. It's actually super simple. It turns out to just be R divided by 100,000 in this case. Sorry, 10,000. So 10 to the 4th. That is the number of numbers, between 0 and R minus 1 that end in 4 9s. It's just R divided by 10 to the 4th. And you take the floor, obviously. So that's a pretty important insight. It's actually, the way we're going to do this problem is we're just going to loop over the number of digits, and we're just going to count how many numbers change at least this many digits, and then we're just going to add that up for every number. So in particular, this is equal to the number of the count of numbers between 0 and R minus 1 that end in 4 9s, right? And this is 4. So actually the answer to this function f is actually just R, because there are R numbers that change at least 1 digit, plus 4 of R divided by 10, plus 4 of R divided by 100, and so on. We just add all those up. And obviously we can stop once we reach 10 to the 9th, because once we go past that, it's always going to be 0. And yeah, I mean, that's just the solution. It's really simple. You just read in L and R. You go from 10 to the 0 up to 10 to the 9th, and you just add R divided by base. And I could have written this function f, but I just decided to just make it simple and do this loop like this. we subtract out L divided by base for this reason. And then we're just multiplying by 10 each time and then outputting that answer. So super simple solution, super fast, but it definitely takes some, solid thinking about what we're really trying to count to get there. Okay, so that was F. Now we can look at G. So I found G a little bit tricky. There's a couple details here. So basically you've got X red candies and Y blue candies. You want to make gift bags. Each bag, you have two options. Either you can put A red candies and B blue candies, or you can put A blues and B reds. And you want to know the largest number of gift sets or gift bags you can create. Right, so for example, if these are the values of X, Y, A, B, you can make 3 gift sets. You do one of the first set and then you do 2 of the second set. And then what happens is you've used all your Y and you have 1 X left over. So you did a good job of just distributing them across the gift sets. And then, so you have 10 to the 4th test cases. And in each test case, the values are between 1 and 10 to the 9th. So again, relatively big values, we need to do something efficient. In general, with these types of constraints, you want to do something, at worst, some sort of log or log squared time, that type of thing. Okay, so first thing to notice with this problem is because of the nature of this, you can just swap X and Y if you want. You can also just swap A and B if you want. So first thing I did was to just make sure X is less than or equal to Y and A is less than or equal to B. Just make sure they're in a certain order. Makes it a little bit nicer to deal with. And I actually think the maybe most straightforward way to think about this problem is you can think about binary searching on the answer. So let's say we have a number K and we want to know, can we make K gift sets? So then what we get is we get this nice setup. Can we make K gift sets? Well, so X is less than or equal to Y, A is less than or equal to B. So in particular, we know we have to take out K times A from both. So X, Y, we're going to turn them into X minus K times A and Y minus K times A, K times A. And so maybe X prime, Y prime. So now we have X prime and Y prime, and then basically instead of A, B, we have 0 and B minus A. Let's call that D. So now it actually turns out to be quite simple, the number of, the way to distribute these gift sets. So in particular, what I just did is I converted AB equals AA plus 0D. And since we've already decided on K, we might as well subtract out this AA from X, Y, K times. And then after that, we're just deciding whether we want 0D or we want D0 and how many of each we want. And yeah, once you get to this point, this is super simple. I mean, the number of gift sets we can make is just going to be this plus this, right? Which is, clearly the best you can do with these options. And we just need to check, is this at least K? Yeah, so then you just binary search on K, find the largest K where it is possible, and then you're good to go. And that's log time. I actually, in contrast, I wrote a solution that is O of 1. So it's based on a lot of the same idea. Basically, what we're going to do is, first of all, if A equals B, then we just do X divided by A. That's super simple. But otherwise, what we're going to do is we're going to try to equalize X and Y first, greedily. And we're going to do, we're going to take A, B in that order from X, Y, kind of over and over until either we run out or they get very close to being equal. So we're basically trying to reduce this XY diff with the AB diff, and we do as many times as we can until we reach kind of the minimum. And then once we get to that point, then we're just going to try to do pairs of AB and BA to just make both sides equal. And that's what we do here. And they both take out together times a plus b. And then after that, since we can no longer do both an AB and a BA, the only thing we can do left is do some more ABs, and then we're just going to add that. And basically the reason that this works is it's a lot of the same logic where, yeah, essentially you're just trying to kind of order the AB versus BA in a way that kind of gets just the right amount to get them to about equal. Let me think about how to explain this in a way that might be more thorough. Yeah, I guess kind of the main thinking is that there's going to be some number of ABs, there's going to be some number of BAs, and with the overlap, you know, once we're done, you get to essentially just a certain number of ABs left, extra ABs, and that set of ABs, it's just like, no, I don't know if that's the best explanation. Yeah, I guess maybe the best way to explain it is just, yeah, a pretty simple greedy where as long as taking another AB from XY in that order doesn't reduce Y below X, there's no reason you shouldn't do that and just like keep them that way. And then once they get to near equal, meaning another X or another AB would reduce Y below X, now you get to the point where you just want to essentially go back and forth to AB and BA, and then yeah, you might have essentially you just have potentially one more at the end, I think. Yeah, so maybe that's not like the best explanation. I think this binary search explanation is a lot kind of clearer in terms of the rigor. I guess maybe it comes down to this breakdown again. Yeah, I think that's really just what it is. It's just this breakdown again. And even if you don't do this binary search, you can still think of it this way where, you know, how exactly are you going to do this? Well, if we think greedily, we're just going to, like, which one should we reduce by D, X prime and Y prime? Well, we should just always, greedily, we should just always reduce the bigger one. And yeah, I mean, that's essentially what this whole strategy is doing. This reduces the bigger one until they're about to swap in order and then alternates. And then we just check if we can do one more. And so that's the main idea. So that's why it's basically the same greedy idea. There's another kind of more jinky solution with ternary search that I did. I'm not going to explain it because it's not super great, but I actually got wrong answer with it the first time before getting AC with it. I haven't like proven it. Maybe it's not actually even correct. It's possible. But a couple different ways you can approach this problem. All right, so last we have problem E. Is it still the lowest? It is. It's still the least solved problem. And actually, wow, F has way more solves than D. So that's actually crazy. I guess maybe one thing about F is it's a little bit more guessable, especially because this test case kind of gives you some ideas with the 1, 1, 1, 1, 1. But anyway, so on to problem E. So we've got a certain programming language. There's only two types of statements. The first statement, you assign a variable a string value. So var, so this is colon equals. Var colon equals hello, assigns the variable var the value hello. And then x equals a plus b, it assigns the variable x the concatenation of these two variables a and b. So if a colon equals hello, b colon equals world, and then c equals a plus b, c will become hello world. It's guaranteed the program is correct, and all the variable names and strings are only consisting of lowercase letters and don't exceed 5 characters. And you want to know the number of recurrences of the string haha in the very last variable. So you need to calculate this, and there's up to 10 to the third test cases. Each test case has up to 50 statements. And 50 statements is actually enough to do a lot of damage, basically. And they show you this example when they do this example case. You can just double your string 50 times, right? And 2 to the 50 is huge. We don't want to actually generate any of these strings in that case. Right, so n equals 15, the answer can be huge, right? If n were 50 and they did this, the answer would just be, gigantic. So we need a more clever way to solve this problem. And yeah, the key idea is, first of all, haha is not a very long string. It's only 4 letters. And so basically there's a clever idea here. And the clever idea is when we take these strings or these variables, we have a certain format that we can use to represent them. And the format just consists of a couple things. It's the length, the number of ha-has, and then kind of a first and last. The first 3 characters and the last 3 characters. So why do we do first 3 characters and last 3 characters? Well, when we do x equals a plus b, the length, super easy to update. We just combine the lengths together, right? In fact, maybe I didn't even need this variable, the length variable. And the haha, the number of ha-has is just going to be the number of ha-has in A plus the number of ha-has in B. And then we have this tricky thing where there are some ha-has that can cross between A and B. And if we think about this crossing, so, maybe ha-ha-ha, right? If we think about this crossing, there are only a couple options. We can take 3 from A and 1 from B. We can take 2 from each, or we can take 1 from A and 3 from B. And that's why we keep the first 3 letters and the last 3 letters. So when we are doing a concat on 2 variables, we're making a new variable z. The length is the sum of the lengths. The haha is the sum of the ha-has. But we're also adding the number of ha-has between basically x dot last plus y dot first. So the last 3 and then the first 3. And we're counting the number of ha-has that cross. And then these just kind of update the first and the last and do a trim. So this trim makes sure this size is at most 3. So this is the key idea. This keeps it. This keeps the state size constant instead of ballooning, exponentially to 2 to the 50. Yeah, and then all it's left to do is just implement the language. We have a map from string to variable object, and we're just going to take care of all the cases. Either we init a variable with this string, or we do the concat between A and B. And then finally we output last.haha. So yeah, so the key idea here is it's kind of this clever idea of how do we represent the variables to count the ha-has without actually storing the entire string. And yeah, the key idea is, when you have a huge string, most of the middle doesn't matter. It just matters how many ha-has there are and then what the first and the last few characters are. Okay, so that's all the problems. And that'll be it for me today. But yeah, how did you do? How did you do in this contest? This is definitely a tougher Div 3 contest. I think they even mentioned it in the description. Yeah. They actually made it 15 minutes longer. But yeah, what did you think? Let me know in the comments. And if you want to be updated for future videos, leave a like and subscribe. And I will see you in the next one.